This video, we're going to go over the multiple choice review from the review number 1 for our AP Stats review packet. Let's get started. Height in meters is measured for each person in a sample. After the data are collected, all the height measurements are converted from meters to centimeters by multiplying each measurement by 100. Which of the following statistics will remain the same for both units of measure? All right, so the mean of the heights will not stay the same because mean will get times by 100. So that's not going to work. Same with the median. Multiplication affects the spread. So that's going to also change the spread too. So it's not going to do that. The maximum height of the measurement, sure, because it'll be 100 times. So they're all going to be times 100. The only thing that'll change is the Z-scores, or that won't change. That's going to be the same because Z-scores remain constant, right? Z-scores are always centered around 0 and have a standard deviation of 1. Okay, that'll always be true. So just think about that. Z-scores always kind of center around 0, standard deviation 1. Okay, question 2. A candy company produces individually wrapped candies. The quality control manager for the company believes that the weight of the candies is approximately normal, distributed with a mean of 720 milligrams. If the manager's belief is correct, which of the following intervals of weights will contain the largest proportion of the candies in the distribution of weights? One thing it does not give you is a standard deviation, but that's okay. So let's just kind of eyeball this, all right? If it's centered around 720, then you want to go, which is going to give you the largest proportion? We want to look for the biggest area under the curve. So let's think about, I don't know, let's say 740 to 780. That's going to be somewhere over here, right? So I don't know, somewhere over there. Let's think about that. Let's do the next one here. 700 to 740. Well, 700 is down here. 740 is above it. That's a little bit bigger, wouldn't you think? Let's do 680 to 720. 680 to 720, you know, who knows where 680 is. Now 680 is a little bit below. Now it's kind of hard to tell, you know, in my drawing here, which one is going to be bigger, right? So let's kind of think about that as we do the other one. 660 to 700. 660 to 700, well, that's going to be below here. 660 is here. Probably not going to be that one, right? So we can kind of eliminate this one and that one. And then 620 to 660, heck, that's going to be worse, right? Because 620 to 660 is even further out. So we're talking like here. So let's talk about these two for a second. Even though I'm not given a standard deviation, make one up. I mean, if you want to know exactly what that is, let's say the standard deviation is, a reasonable standard deviation for me would be, it looks like everything's counted by 20. So I'm just going to say, all right, let's standard deviation be 20. Now, what I want you to do, it doesn't really matter what standard deviation is, go to your normal CDF. All right, click on normal CDF, and let's test this out. So let's put second vars, 2 for normal CDF, and let's do the B. 700 to is my lower, and then my upper would be 740. All right, just kind of get a sense of that. It doesn't really matter what the mean standard deviation is. So you could the mean has to be 720, right? We know it's centered around 720. That part's important, but the standard deviation, it doesn't really matter. Let's just make it 20 to be easy. All right, so think about that. That is 68%, right? It's about 68%. Now let's do it with the 680 to 720. %. So this is 68%. This is about 48%, right? So this one's actually bigger. Okay, so make up a standard deviation and then plug it in a normal CDF and use the lower and upper bounds given. And you can check that. 700 to 740 is our best estimate. And just so we can verify here, like, why did I use 20? It doesn't really matter. I could have done 680 to 720. I could have kept that at 720 and did, I don't know, 1. And that's 50%. And then if I did second normal CDF, I did 680 to 720, if I did 700 to 740, well, look at that difference, right? 700 to 740 is way bigger than 680 to 720. So if you lower that standard deviation down, man, you'll get it right. But again, I use 20 because it seemed like a reasonable standard deviation. Either way, that's the bigger number. All right, question 3. In this question here, we want to know the amount of time for 100 mice to navigate through a maze was recorded. The histogram below shows the distribution of times in seconds for the 100 mice. Which of the following values is closest to the standard deviation of the 100 times? All right, so let's see. We have the center is around 90. Center around 90. So let's assume this looks pretty fairly normal curved. All right, it's roughly normal, approximately normal. It's centered around 90. So let's just say the mean, well, we'll use X bar, is roughly 90. Could be a little bit more or above, but let's say it's roughly 90. Now, if I want to know a standard deviation, think about when I'm going out, roughly 1 standard deviation away will get me 68% of the data. 2 standard deviations away gets me about 95%. And then 3 standard deviations away gets me about 99.7%. So if I just kind of eyeball it, it looks like it's going from 90 out to 80 and 100. That roughly contains approximately 68% of the data, right? So I would say that my standard deviation is 10 seconds. Definitely not 2.5 seconds, because 2.5 seconds, that's too small, right? That's going to be over here. That's not 1 standard deviation. And then 20 seconds, that's too much, right? That contains way more than 68% of the data. 50 seconds, 90 seconds are just way too big. So it's definitely going to be 10 seconds on this one. All right, for question number 4, I have a little diagram drawn for it. A graph not shown of the selling prices of homes in a certain city for the months of April reveals that the distribution is skewed to the left. Which of the following statements is the most reasonable conclusion about the selling prices based on the graph? So I went ahead and drew a couple of skewed left diagrams to kind of get you an idea. The tail is always going to go this way. And in a box plot, you know, you'll have a longer whisker typically, and maybe one half of the box might be longer than the other. So let's look at letter A. The mean is greater than the median. In skewed distributions, the mean is always going to be pulled toward the skewness. So the mean might be here, whereas the median might be there. So in this case, the mean is less than the median. That's not going to be true. The median is the average of the first quartile and third quartile. Well, look at the box plot. The median is not the average of those quartiles, because typically this might be a larger than this value. So it's not right in the center. So it's not going to be the average. Letter C, there are fewer selling prices between the first quartile and the median than there are between the median and third quartile. Again, that's typically the opposite, all right? There's usually more here than there. So that's not going to be true. There are more selling prices that are less than the mean than selling prices that are greater than the mean. There are more selling prices that are less than the mean than selling prices that are greater than the mean. While that looks tempting to answer the question, that is actually not necessarily true. There could be more selling prices. There could be a whole, there are more selling prices that are less than the mean. Oh, no, there's got to be more that are greater than the mean, than the median, than less than the mean. Yeah, more. There are more selling prices that are. This is flipped, so reverse. That's not true. So this is to E. The value of the maximum minus third quartile, this value right here, is less than the value of the first quartile minus the minimum. That is true. Less, more. So that is true. The value of this value is less than that value. That's how skewness works. All right. All right, question 5. If a probability distribution is symmetric, which of the following statements must be true? The distribution is normal. Not necessarily the case. Take a look at this one here. That is not normal. You can make a symmetric bimodal, so boom. The distribution is uniform. That's uniform. There's no way the distribution has to be shaped. The distribution is bimodal. It doesn't have to be bimodal. It could be one unimodal or normal. The mean of the distribution is equal to the median. Well, if it is symmetric, the mean, there's no skewness. The mean and the median will be in the same spot. So that is true, whether it's uniform or bimodal, the mean and the median will always be in the center if it's symmetric. So that's going to be true. Let's look at the last one. The interquartile range of the distribution is equal to the standard deviation of the distribution. Those have nothing to do with each other. So we can rule out that. IQR is a specific value. Standard deviation is a specific value. IQR is based off quartiles. Standard deviation is based off means. And nope, not going to be the same. But the mean and the median of the distribution are going to be the same in symmetric data. So very kind of straightforward question on that one. Okay, question 6. The number of hurricanes reaching the east coast of the US was recorded for each of the last 10 decades by the National Hurricane Center. Summary measures are shown below. So you got your min, max, lower quartile, upper quartile, median, and n, which is the number of data points. So, lower quartile, we usually say Q1, upper quartile, we'll say Q3. Which of the following statements is true? The smallest observation is 12, and it is an outlier. No other observations in the data set could be outliers. The largest observation is 24, and it is an outlier. No other observation in the data set could be outliers. But 12 and 24 are outliers. It is possible that there are other outliers. 12 is an outlier, and it is possible that there are other outliers at the low end of the data set. There are no outliers at the high end of the data set, and 24 is an outlier. It is possible there are other outliers at the high end of the data set, but there are no outliers at the low end of the data set. We got to use the 1.5 IQR rule. So what you want to do on this one is you want to get the IQR, which is Q3 minus Q1, multiply that one by 1.5, and then subtract it from Q1, add it to Q3. So let's do that real quick. The IQR is 18 minus 15, which is 3. If you times that by 1.5, you get 4.5. Subtracting 4.5 from 15, you get 10.5. Adding it to 18, you get 22.5. My decimal didn't show up. So that means outliers are anything below 10.5, and then above 22.5. Well, let's look at my minimum value. My minimum value is 12, so there are none that are below 10.5. So there are no lower outliers. But we do have a maximum value of 24. So 24 is an outlier. Is it the only one? Not necessarily. Well, let's take a look. I mean, we have 24 as an outlier here, but does that mean that there isn't a number like 23 or 23 and a half? No, there could be other outliers. 23 could be an outlier, but we don't have all the data points, right? So there could be a 22 and a 23, 23 and a half or whatever, but we know 24 is an outlier, and there could be others. So let's take a look and which is the best one. 24 is an outlier, and it is possible that there are other outliers at the high end of the data set. That is what you want to pick. It's not the only one, okay? Because we don't have all the numbers, but it's possible. It is possible that there are other outliers at the high end of the data set. So it's going to be E. Okay, question 7 is technically not in unit 1. So this can be saved for later, but I'm going to go over it anyway. This is actually a random variable, so this would be unit 1, 2, 3, 4. This is going to be in the probability unit, but I'll go over it. Actually, this would be in unit 5. This is sampling distributions. So two friends, Andy and Bob, participate in a game of bowling every week. From past experiences, it is known that both friends' scores are approximately normally distributed, where Andy has a mean score of 150 with a standard deviation of 30. Bob has a mean score of 165 with a standard deviation of 15. Assuming that their scores are independent, which of the following values is closest to the probability that Andy will have a greater score than Bob in a single game? We want to realize first is that these are the two distributions overlaid, kind of. I put Andy's, he's got a bigger standard deviation. Notice that Bob is higher in his mean, that's 165, with his standard deviation of 15. So it's going to be narrower. Mean's going to be shifted higher. It's going to be narrower. But we're combining this into one game where they're both playing. So what we have to do is we have to combine their games. We're trying to figure out Andy wants to be greater than Bob. So we're going to do the difference, okay? We're going to get that mean difference of negative 15. And we're going to combine their standard deviations. So remember, when you combine standard deviations, you actually have to square them and add them together, then take the square root. So you think about taking Bob's and you got 30 squared. And then you're going to add that to, or not Bob's, Andy's 30 squared plus Bob's 15 squared. And that's their combined variances. And then we have to square root that. And so that's where the 33.54 comes from. So we create a new distribution with a single game where it's centered around negative 15 with a standard deviation of 33.54. Now the question is, what is the probability that Andy is going to have a greater score than Bob in that single game? Now we can do a normal CDF. Again, this is not in unit 1, so this is more of a sampling distribution. I said random variable, sampling distribution question. So we want to do normal CDF. And then our lower is going to be, well, if Andy's greater than Bob, we want to say greater than 0 is going to be 0. And then our upper is going to be infinity. Our mean is going to be negative 15. And our standard deviation is going to be 33.54 approximately. That's what's going to get you your answer. So it's going to be one of these answers here. Let's see what we get. So 0, infinity, 1899. Mean of negative 15 with a standard deviation of 33.54. That part's important. We got to, since we're combining their efforts into one game, we have to combine the standard deviations. So it's about 0.327355. So approximately 33%. Approximately. So 33% would be your closest answer to that. But that, again, that's a later unit. All right, number 8. Zucchini weights are approximately normally distributed with a mean of 0.8 pound and a standard deviation of 0.25 pound. So standard deviation of 0.25. Which of the following shaded regions best represents the probability that a randomly selected zucchini will weigh, sorry about that typo, between 0.55 and 1.3 pounds? So let's think about our mean here having to be 0.8. And this is the mean minus 1 standard deviation. This is the mean plus 2 standard deviation. So let's do a little subtraction. So we have 0.8. If I subtracted our standard deviation of 1.3, of 0.25, so 0.8 minus, let's check A out first, minus 0.25, since I want to go one below. Let's see. Put that in your calculator if you need to. And so that's going to be 0.55. And if I add, so that's going to be 0.55. And if I add 2 standard deviations, so if I do 0.8 plus 2 times 0.25 or 0.5, well, that's 0.5. 15 plus 8, or let's see, is it 0.5? 5 plus 8 is 13, 1.3. That should be 1.3. You can double check that. And oh, look at that. We are in luck. It's between 0.55 and 1.3. That's exactly what this is right here. So I'm not even gonna worry about the other ones. We got lucky, we got the first one. I'm gonna move on. Okay, question number 9. Question number 9 has a typo. And that's in the correct answer, but I'll go over the answers. This should say fertilized. So the median for the unfertilized trees is less than the median for the, your paper says unfertilized trees, but it should just say fertilized trees. So let's just get that out of the way now. That will be your answer. I'll go over how to get it. So the figure above summarizes the heights in centimeters of approximately 400 pine seedlings 6 years after they were planted at a Center for Environmental Study. Approximately half of the trees were fertilized yearly, and the remaining trees were never fertilized. Which of the following statements about the medians and interquartile range of the heights of the two groups of 6 trees after being planted is true? So let's look at A. The medians and IQRs are the same for the unfertilized trees and the fertilized trees. Right off the bat, those are your medians. Those are different, so that's done. The median for the unfertilized trees is greater than the median for the fertilized trees. In fact, it is less than, that's less than that median. So that's no good. C, the median for the unfertilized trees is the same as the median for the fertilized trees. Again, they're different. The medians are different. Let me go to the other wrong answer. The median for the unfertilized trees is less than the median for the fertilized trees. That's true. And the IQR is less for the unfertilized trees. Well, even though the median's less, the IQR between the unfertilized and fertilized is actually greater. So the unfertilized versus the fertilized. So those are actually all wrong, except for this one, if you fix the typo. The median for the unfertilized trees, so let's go to the right answer. The median for the unfertilized trees is less than the median for the fertilized trees. That we know is true. And the IQR is greater for the unfertilized trees. That is also true. So the IQR is greater for unfertilized trees. Sorry for the typo, but it is going to be that one. Take the un away. Okay, this question is challenging because it's conceptual. You have to think about it real hard. A certain motel is roughly 20 miles from the entrance to Yosemite National Park. Always wanted to visit there. The motel manager wants to get a better estimate of the distance and asks 5 people to each measure the distance, the nearest tenth of a mile, using the odometer in his or her car. Her. The manager will use the median of the given measurements, all these typos, as the estimate of the distance. Which of the following statements is not a statistical justification for the manager's plan? So A, odometer reading should be considered a variable when used to measure the distance. Odometer reading is a variable when used to measure the distance. Okay, because we don't know what it is, right? So it's unknown. I buy that. The median of the 5 measurements is more likely to be close to the actual distance than a single measurement. Well, yeah, when we want larger sample size. So yes, a bigger sample will yield a more accurate result. We know that's true. C, the actual distance should be considered a variable. And take time out, the actual distance is not a variable. That's a parameter, that's set. Doesn't change. The actual distance, what we're trying to measure, is not a variable. The 5 measurements can change, but the actual distance doesn't change. So that's actually the one that's not true. D, if 1 or 2 odometers give inaccurate readings, the estimate still should be fairly close to the actual distance. Well, if you have several different measurements, then yeah, that could be true. The manager can get some indication of how far off the estimate might be. True, but guys, the parameter is what we're trying to figure out. That's not a variable, so it's going to be C. Okay, question 11. The distribution of heights of 6-year-old girls is approximately normally distributed with a mean of 46 inches and a standard deviation of 2.7 inches. I have that drawn out here. We'll do a little bit of shading on there. Aaliyah is 6 years old and her height is 0.96 standard deviation above the mean. Now, let's pause for a second. That's your Z-score. Her friend Jane is also 6 years old and is at the 93rd percentile. That's 93% of the data is below whatever her height is. Well, that's hers. Hers is actually easier to get first. So we're going to get Jane's her value by using the inverse norm. So what I want you to do is you're going to go into your calculator and you're going to do second vars 3. And 93rd percentile is 93% below wherever she is. So 0.93, we'll go there. And we have our mean, which is 46, and our standard deviation, which is 2.7. And it'll go to the left. You don't have this left, center, right option on your calculator, so just keep that left. And Jane's height is 49.98. Okay, that's Jane's height. 49.98. So again, we're just going to do inverse norm, 0.93, 46, and 2.7. So that's her height. Now let's look at Aaliyah. That's a little bit more complicated. So that Z is the Z, that 0.96 is the Z-score. So we're going to have to actually solve this equation. So we're going to multiply by 2.7. Multiply everything by 2.7. And you know, a Z is X minus whatever the mean divided by standard deviation. So what happens is those cancel out. 2.7 times 0.96. What is that? So 2.7 times 0.96 is 2.592. Then we're going to have to add the 46. So let's do that. And that's going to be 48.592. So Jane's height, or Aaliyah's height, we know Jane's 49.98, but Aaliyah is going to be 48.592. So Aaliyah is going to be shorter than Jane. She is going to be shorter than Jane. So we can rule out the taller than Jane and taller than Jane. So let's figure out her percentile, okay? Aaliyah's height is it in the 17th, is it in the 67th, or the 83rd percentile? Well, let's see, 48.592, we can get her percentile by, we can do some normal CDF. So 48.592, I don't know what that is, but we know that at 48.592 and everything below, we can figure out the area underneath 48.592, and then we can get the percentile for that, the percentage. So we're going to do second vars, normal CDF for that. Our lower is negative infinity. Our upper would be 48.592. And our mean is 46. And our standard deviation is 2.7. So Aaliyah's percentile is the 83rd percentile, believe it or not. So she's at the 83rd percentile. And again, normal CDF. The negative infinity to 48.592 mean would be 46, and the standard deviation is 2.7, and that is going to be approximately 0.83. So Aaliyah is going to be at the 83rd percentile, and she still is shorter than Jane by about 1.5 inches. There you go. Okay, question 12. For the 3 histograms above, which of the following correctly orders the histograms from the one with the smallest proportion of data above its mean to the one with the largest proportion of data above its mean? All right, smallest above its mean. So let's look at these 3. The mean would be, I'm just eyeballing it here. So for number 12, the mean would be here because it's skewed right. So it's a little bit further to the right. Pretty small proportion above. For this one, the mean would be pulled this way, right? And for this one, the mean is, well, it's roughly symmetric, so it's going to be right here. So I would say this has the largest amount above because it's skewed left. This one has the smallest amount above. And this one is kind of in the middle, right? This is your mean here, so middle. So this one says, which of the following correctly orders histograms from the one with the smallest proportion of data above its mean to the one with the largest proportion? So smallest would be J. So J is going to go first. And then it's going to skip here. So this is going to be like smallest. So it's going to be first. Then middle is going to be this one here. So it's going to actually skip to L. And then the largest above would be this one because it's skewed left. So it's going to be K, J, L, K, J, L, K. So it's going to be B. I like that one. Okay, 13. Which of the following dot plots, which represents the set of data that has the greatest standard deviation? Ooh, kind of tricky here, but standard deviation is on average how far the typical point is from the mean. So they're all symmetric. Look at that. They're all symmetric, which means the mean here is going to be 5 for all of them. So on average, which graph has the typical point the furthest away from the mean? Well, it's going to be B. You don't have any points in the center. So this is going to be the most spread out, okay? Even though these are all perfectly lined up, it's going to have a smaller standard deviation because it's very evenly spread out. But this is no points in the center, furthest spread. That's going to be the highest standard deviation. Okay. This one's next one right here because it only has 2 in there. All right. That was nice. Okay, question 14. Random sample of 374 United States pennies was collected. The age of each penny was determined. According to the box plots below, what is the approximate interquartile range, IQR, of the ages? Well, interquartile range is Q3 minus Q1. So we got to estimate these here. Let's see here. It looks like it's just slightly under 20. And this one is, I don't know, 4 or 5, something like that. So let me just say, I don't know. Let's say it was 19 and 4. Or 3 or something like that. I can't really tell. Or it could be 20. Maybe closer to 20. 20 and 4. I don't know. Either way, we can roll out these two. Like 20 minus 4, obviously not going to be 40 or 50. 16, 10's too small, right? Like it would have to be more like that for it to be 10, and 8's just way too small. So 16, now I just eyeballed these. It could be 19 and 3 or 19 and 5. It could be 19 and 5, right? And 19 minus 5 is 14, but it's still closer to 16 than 10. So it says, what's the approximate interquartile range? Approximate, just the one closest to. Okay, it doesn't have to be exact. Closest to would be 16. $15. That's probably the quick, easiest one on here if you know your skewness. It says, histogram above shows the number of minutes needed by 45 students to finish playing a computer game. Which of the following statements is correct? Is it skewed to the right? Well, skewed right looks like this, so no. Is it skewed to the left? Skewed left looks like that, so yeah, skewed left. That's the one right there. Distribution is normal. Nope, that's not. Come on, normal. Chi-squared, get out. We ain't doing chi-squared. Uniform looks like this. And by the way, chi-squared is this weird, distribution looks like that. It's very right skewed. The only one that makes sense is skewed to the left. So it's that one there. Okay, question 16. The commuting time for a student to travel from home to a college campus is normally distributed with a mean of 30 minutes and a standard deviation of 5 minutes. If the student leaves home at 8:25 a.m., what is the probability that the student will arrive at the college campus later than 9 a.m.? So Let's see. Think about this. Normally distributed, mean of 5. Later than 9 a.m., how many minutes is that? Well, let's see. We're going from 8:25 to 9. That's 35 minutes. And we want to know the probability later, keyword here. So we know the probability is going to be greater than 35 minutes. So we're looking for this. Let's see, 30, 35 here. Standard deviation is 5. Should be about 16%. So we're going to do normal CDF. Lower is going to be 35. Upper is going to be infinity, 1E99. Mean is going to be 30, and standard deviation is going to be 5. So let's do that here real quick. Normal CDF. Get my face out of the way. Second bars, 2, 30. Upper 1E99. Remember, that's going to be your infinity. Anything above that. And I put 30, that should be 35. Gotta be careful there. Your mean is 30, and your standard deviation is 5. All right, let's get that in there and see what we get. So about 15.86%, 0.1586 is 16%. There you go, guys. Okay, question 17. The histogram below displays the frequencies of waiting times in minutes for 175 patients in a dentist's office. 175 patients in a dentist's office. Which of the following could be the median of the wait times in minutes? Well, let's review how to do that, shall we? The median is the middle. So let's just take that 175 and cut that in half. What do we get? Well, 175 divided by 2 is 87.5. So let's look at our frequencies. Remember, this is a histogram. This is the counts. This is your frequencies. Well, this is at 80 right there. So that means I got to go 7.5. And we're at 40, somewhere between 40 and 60. Maybe that's about 50 or so. 87.5, that's going to be somewhere in here. So it's going to be somewhere between 5 and 10. I don't know the exact number, but it's between 5 and 10. That's good enough for me. 7.25. That's it's a possible median. Okay, 18, data were collected in the amount in dollars that individual customers spent on differ in an Italian restaurants. I have no idea what that is. The quartiles of these data are given below. Q1, Q2, Q2's median. I don't know why they do that. Q3, 58.97. Which of the following statements must be true for these customers? At least half of these customers. Okay, let's get a box plot going on. I don't care if it looks symmetric or not. We don't know our min, we don't know our max, but we do know these three numbers. We know 36.27, we know 44.27, and we know 58.97. What's up with the sevens? Are your meals costing that much? All right, so in a box plot for you that need a refresher, 25% of your data is here. 25% is here, 25% is here, and 25% is there. All right, now let's answer the question. At least half of the customers spent less than or equal to 44.27, and at least half spent greater than or equal to 44.27. Well, I mean, that's right. Hold on, let's look at the next one. 75% of the customers spent between 36.27 and 58.97. That's 50%. 50%. So no. 25% of the customers spent less than or equal to 58.97. No, that's 25. The mean amount spent by customers is 44.27. Okay, we don't know if it's symmetric, so mean is not equal to the median, unless we're specifically told it's symmetric. A majority of customers spent $44.27. A majority of customers, there could have been one person. That's not a majority. So yes, half spent less than the median, the other half spent above. This is 50%, half. This is the other 50%. And there's your median. Sorry for the scribble. That's 18. Okay, the 19, the weight of adult male grizzly bears living in the wild in the continental United States is approximately normally distributed with a mean of 500 pounds and a standard deviation of 50 pounds. Boom. The weight of adult female grizzly bears is approximately normally distributed with a mean of 300 pounds and a standard deviation of 40 pounds. Boom. Approximately, what would be the weight of a female grizzly bear with the same standardized score, Z-score, as a male grizzly bear with a weight of 530 pounds? Well, guys, we gotta get some Z-scores going on in this thing. So let's get the Z-score for the adult male since we have the adult male's value. So Z for the male, well, it's going to be, let's see, 530 minus 500 divided by 50. So that's going to be 30 divided by 50. That Z-score, 3/5, what is that, 0.6? Double check me in the calculator, but there's your Z-score. So now let's do the female. So female, we just work backwards, right? We have the Z for the male, which happens to be the Z for the female. All right, so we're going to just say 0.6 equals, but we don't know the special value. We know the mean for females is only 300 with a standard deviation of 40. So we're just going to work backwards. We're going to multiply by 40 and add 300. So take a minute to do that. We're going to multiply 0.6 by 40. Here, let me do that here. 0.6 equals x minus 300 divided by 40. 0.6 times 40 equals x minus 300. Let's see, 6 times 4 is 24, so that should be 240. 24. Yeah, it should be 24. Double check that. And then we're going to add 300. So that should be 324. And there you go, guys. 324 pounds for that female. All right, our last problem on here. I should point out that these two are the same. One of them is a typo. I'm not sure which one's wrong, but let's just go through the problem with that. Keep that in mind. For a sample of 42 rabbits, the mean weight is 5 pounds, where the standard deviation of weights is 3 pounds. Which of the following is most likely true about the weights of the rabbits in the sample? Well, let's think about the distribution. So we have 42 rabbits. The mean is 5 pounds. So let's say we have a mean of 5. Standard deviation of weights is 3 pounds. So that's talking about going down to 2, -1, -4, 8, 11, 14. Okay, does that make sense? The mean is 5. The standard deviation is 3. Only got one problem here. Think about rabbits or anything. There's no such thing as a negative weight, right? So it kind of gets cut off, right? So you might have a bunch of stuff up here, and then it kind of tails off. Well, guess what, guys? That's going to be skewed, right? It can't be normal in this sense because you have within 2 standard deviations, you have most of the stuff in here, right? But there's no negative weight. Just think about the context of the question, all right? You can't have, in some situations, you just can't have certain values. You can't have a negative weight in this case. So it's going to be skewed right. So it's skewed to the right because the least possible weight is within 2 standard deviations of the mean. That is true. The least possible weight is within 2. It's 1.5 standard deviations away from the mean, or not quite, but it's within 2 standard deviations of the mean. But these are the same thing. So either one of those is the right answer. I'm not sure what's going on there, but C or D. Thank you for watching this. I hope this was helpful. Again, if you've gone through this already and you've Try it on your own. Don't erase your work. Just, you know, check it off and re-answer it and make sure you have work to go along with it. Bye.